Well, hello Internet, and welcome to part 9 of my Java algorithms tutorial. Today, because I had a little bit of time set aside, I decided to cover a question I've been getting a lot. And in this tutorial, I'm going to explain in a simple way what exactly we mean by big O notations. And just to cut to the chase, big O notation is a way to measure how well a computer algorithm scales as the amount of data involved increases. So how well would it work in, say, if it was using a 10 element array versus a 10,000 element array? As you're going to see here in a second, it's not always a measure of speed, but instead a measure of how well an algorithm scales. And this is going to be a rough overview of big O, and I'm not going to cover topics such as asymptotic analysis and other things that have to do with discrete mathematics. I'm going to instead focus on the simple idea. So I got a lot to do, so let's get into it. Okay, so I'm doing a lot of this out of my head here, so bear with me. But basically, what I want to do here is give like a little example. So let's say we have 45n cubed plus 20n squared, and this is going to be our algorithm we're going to be playing with here, plus 19. Now, if n is equal to 1 in this situation, that's going to come out to 84. And the reason why this is going to be very important is I want to define, with big O notation, the part of the algorithm that has the greatest effect, ultimately, on the final answer. So now in this situation, if n just goes up to being equal to 2, you can see very quickly that your answer is going to go from 84 to 459. And you can also see that it's not going to be that long until 19 doesn't matter. It doesn't have much of an effect on the performance of our algorithm. So we might start to question, is it important at all? Well, then what happens if n goes up to, say, 10? Which we're still not dealing with very large numbers here. You can see the answer to this, it goes up to 47 and 19, which, as you can see, now you're starting to question, well, definitely 19 doesn't really have that much bearing in regards to the final answer. And also, when you think about it, n squared has very little to do with this answer, if in fact 45n cubed is going to be equal to 45,000 in this situation. So if you're going to be dealing with very, very large numbers, you very quickly see that the part of this algorithm that really has a lot to do with the final answer as this data set scales is not even going to be the 45, but it's going to be the n cubed. And hence, we would say that this has an order of n cubed. And that is just a very, very basic look at this and something to think about as things go on and what our ultimate goal with big O notations are. So let's come in here and I'm going to write some code, and I'm just to show you, I'm going to go over order of 1 and what that means, and I'm going to go over order of n and what that means, order of n squared, provide examples what that code looks like, as well as n cubed and all these other ones. Also going to get into log n and order of n log n. Okay, so that's what's going to be covered in this tutorial. So I got to get a couple pieces here because we're going to be playing around with big giant arrays. So I'm just going to create myself an integer array, call it the array. Let's say that I'm also going to need array size. And I'm going to be covering a lot of the different things that I've covered in previous parts of this tutorial, like binary search and all that stuff. Items in array, and I'm going to set this for 0 to start off. Static long start time. I'm also going to show you the difference in how long it takes for things to execute, even though, like I said before, big O notation doesn't really have that much to do with speed necessarily. And all the code here is available in a link underneath the video. So the very first one we're going to do, and probably the easiest of these guys to understand, is going to be order of 1. And I'm going to put this in here as a comment. And what this algorithm does, or what this notation means, is it's going to be an algorithm that's going to execute in the same amount of time regardless of the amount of data. Or to put it in another word, it's going to be code that executes in the same amount of time no matter how big the array is. So what exactly would that look like? Well, one example of that in the context of working with arrays would be if we wanted to add an item to an array and an integer was passed over, and we said, okay, we want a new item, and I went in here and said the array items in array plus plus is going to be equal to new item. There you go. That is an example of order of 1. It doesn't matter if this is a 10,000 item array or a 5 item array. It is going to perform in exactly the same way. So that's order of 1. So what would be an example of order of n? Well, this is going to be an algorithm that's time to complete is actually going to grow in direct proportion to the amount of data. And a perfect example of that would be a linear search, which I'm going to show you here in a second. And the reason why a linear search is great for this is to find all values that match what we're searching for. We will have to look in exactly each item in the array. So that would make a big difference if it was a 10-item array versus a 100,000-item array. And in the situation in which we just wanted to find one match, Big O notation is the same because what it's going to do is describe the worst case scenario in which the whole array must be searched. So let's say we're looking for an item that's in a 100,000 item array and it doesn't exist. Well, we want to make sure that we handle that example, which would mean that every single item would have to be searched. So let's just come in here and let's do this with linear search. And a value would be passed in, which would be the value that we're going to be searching for. Boolean value in array. And we're going to mark this as false to start off because we're pessimists and we don't necessarily think we're going to find it. And then let's say I'm kind of doing this just to force the issue so that it searches through the entire array, because the Java compiler is actually smart enough. If I don't tell it that it needs to find more than one, it will actually stop. And then let's just come in here and do a system check to see how long it takes for this guy to execute. And let's say I want to do this in milliseconds. Again, I'm kind of doing this just because I want to point out how long things take to execute and not because Big O notation is really a monitor of speed. And I'm going to give you a perfect example here in a second to show you why speed isn't really the big issue here. And then we're just going to say if the array I is equal to value that we're searching for, value in array is going to be changed to true, and then indexes with value, we're going to add that item to it right like that. And of course put that extra equal sign in there. And then if we wanted to say print something out on the screen, we could say something like value found, value in array, and then throw end time into this to calculate whenever this guy ended execution. And then we could say something like linear search took end time minus start time. And then let's bounce back up into the main function here and do some tests. So Big O notation, test algo, I'm going to just say 2. Big O notation, and let's say I set this for, I'm going to set it for 100,000 as the size of my array. And then I could take this guy here and generate a random number of elements inside of that array, say like that. And I'm going to have to create a constructor for Big O notation because I did copy and paste generate random array into this, but I didn't do it for the constructor, which isn't a big deal. I'm just going to say int size of the array. Array size is going to be whatever was passed into it. And there we are. We just created our new array. Go back up into main and let's create a couple more of these arrays so that we can compare them based off of size differences. So test algo 3, and let's change this to 200,000, and let's create 2 more of them just to experiment with, and change this to 4, this to 5, change this to 4, 5, and then have this be 3 and this be 400,000. And now we're going to be able to come in here and actually perform these linear searches and see exactly what's going on with them, which in essence is going to be to show that they're going to scale as the number of elements that we're going to be using here are going to scale, which makes 100% sense. Actually, I don't even think I need to use all those. And let's file save, and as long as I did it right. And you can see right there with this linear search, this took roughly 4 milliseconds, this took 5 milliseconds, and this took 18 milliseconds. So you can see as the number of elements scale, get bigger, the number of elements we have to deal with, that is in direct relation to the number of elements. And that is why it is known as order of n. So there's an example of order of n. So now let's take a look at what does order of n squared mean, or cubed, or any of these other different things we could put inside of here. Well, this just means that the time to complete will be proportional to the square of the amount of data. And a perfect example of that would be the bubble sort. And this normally happens with algorithms, just like the bubble sort, that have nested iterations, and you're going to see how dramatically that hampers performance as the number of items we have to deal with increases. And the reason why is each pass through our outer loop is actually going to require us to go through the entire list again. So one trip through a loop is going to work out to order of n, but we're going to then have to go through the loop again for every single item in the inner loop. And that is why you get into a situation where it becomes n squared. So let me just show you an example. It'll make 100% sense. So let's just take our bubble sort, public void, bubble sort, and let's say that we also want to monitor the time again that it takes for this to execute. paste that in there, and then let's just paste in this as well. And here it's going to be bubble sort, and there we are. So now our bubble sort, like you saw in previous parts of the tutorial, is just going to be I is equal to array size minus 1, and then we are going to cycle through this as long as I is greater than 1, and then we're going to decrement I, and we're going to have another for loop, and we'll have it set for j. It's going to start at the beginning of the array, and it's going to cycle as long as j is less than I, and then we're going to increment j, and then as we're sorting through this guy, we're going to say if the array item index j is greater than the array item index j plus 1. Well, in that situation, we want to swap values. The items we're going to swap is j and j plus 1, just like you saw previously. Now let's bounce up here and see exactly how that works. So here are our tests, and this is going to be very easy to do. Let's just come in here, get rid of that, and I'm just going to get rid of the second one as well. And here we're just going to run bubble sort on it, and then here we're going to run bubble sort on it as well. And previously when we did the linear search, you didn't see much difference between the first item and the second one. Now you're going to see much more difference. And you're going to see such a difference that I'm actually going to take this down to 10,000 and take this down to 20,000 and execute. And there you can see it took 362 milliseconds and it took 1612 milliseconds. And you can see that it just continues going on here. And how dramatically slower the bubble sort gets depending upon the amount of data. And that is why order of n squared is very bad and to be avoided. So now let's show you an example of another algorithm that is much more efficient, and that's going to be our binary search. And here we're going to focus on order of log n as our big O notation. And this is going to occur when data being used is decreased roughly by 50% each time through the algorithm. And the binary search, like we saw before, is a perfect example of this. And it's pretty fast because as log n increases, or n specifically increases, the increase in log n in comparison to just n is going to be dramatically different. N is going to increase at a dramatically faster rate than log n will. And that is why log n algorithms are very efficient, because increasing the amount of data has little or no effect at some point early on, because the amount of data is halved each time, as we previously had seen with the binary search. Now the only problem with that is that the binary search is going to require us to do a bubble sort, or to sort it in one way or another. So don't have to use the inefficient bubble sort if we don't have to, or we don't want to. So here I'm going to go and create the binary search, and I'm just going to use my search results for my bubble sort just because it's convenient, not because it's good. And you're also going to see here why timing these guys isn't going to really matter, because of how efficient this is. There's not going to be a dramatic difference in speed when the data set for this binary search increases, dramatically even. There'll be almost no effect. So what do we need here? Well, for doing a binary search, we need low index is going to be equal to 0, and high index is going to be equal to array size minus 1. I'm also going to monitor the number of times that we go through this algorithm here, and then we're going to go while low index is less than or equal to high index. Come in here, get middle index. And this is the part that makes it all efficient, where we're constantly cutting the amount of data in half each time we run through it. And then we're going to say if the array middle index is less than value, low index is going to be equal to middle index plus 1. And else if the array middle index is greater than value, then we're going to do the absolute opposite and have I index equal to middle index minus 1. So that's kind of a review of all the stuff we've been doing. Else, we know we got a match. We'll just say found a match in index and whatever the middle index is. Then we'll go low index is equal to I index plus 1, and then we're going to calculate the number of times we went through this whole entire process, and then we'll print that out on the screen as well, just to show you how extremely efficient this search is, times through. And we'll bounce up here. We want to search for a very specific value, and after the bubble sort, test algo 2, binary search for value, and I'm just going to type in 20 in there, test algo 3, search for exactly the same value, and execute. And there you can see 162 milliseconds. This took 721 milliseconds. And now you can start to see why measuring the time doesn't really matter with efficient algorithms, and why big O notation tells you a lot more about an algorithm than how long or milliseconds it would take to execute. And you can also see the efficiency. It only went through it 9 times to search 10,000 items, and it only went through it 10 times to search through 20,000 items. So this is pretty much the picture of efficiency. And I executed it again just so you could see that that was meant to be binary search took 0, not bubble sort. See, binary search took 0. So that is the picture of efficiency, and I hope that makes sense. Because now we're going to look at the order of n log n, which is going to be a little bit more complicated. And that is going to look like n log n. This is the notation that we would be looking for. Now, when we have looked at sorts in the past, they have normally always been, at the very least, order of n. I mean, that has to be. And the reason why is to properly sort a list of elements in an array, we have to look at every single element in the array at least one time. So that's the absolute minimum. However, what we want to try to avoid is something inefficient like n to the squared, which is what we had with the bubble sort. And we already know that the quicksort is much more efficient. But the main answer is going to be, why is it so efficient? Now, to figure out the number of comparisons that we need to make with the quicksort, we first need to remember that it is comparing and moving values very efficiently without shifting, unlike some of the other sorting algorithms we've used in the past. And that means that values are only going to be compared once. They're not going to be compared to each other over and over and over again. So in essence, each comparison will reduce the possible final sorted lists in half. Or to put it in a completely other way, and this is going to be a little bit of math here, the number of comparisons that you're going to have to do is going to equal out to log and the factorial of n. And we already went over what factorials are. And to put that in other terms, so that we can look at this and make more sense of what n log n means, this is going to be equal to log n, which is going to be the greatest value when we're performing our factorial, plus log n minus 1, plus, and it's going to continue on until we finally get to log 1, which is going to be the end of how we're going to calculate our factorial. Put that plus sign in there just to be neat. Alright, so now if we look at this and sort it down, we're going to see that in actuality, comparisons is going to also be equal to n log n. And that is where n log n comes from. Just simplifying this great big giant long factorial that we were calculating right there. So hopefully that made sense. If it doesn't, the code should help you out. So I'm going to do a quick sort right here, real quick sort, and it's going to get the left side of my array, and it's also going to get the right side of my array. And I'm going to say if right minus left is less than or equal to 0, return, because I'm done working with this guy, it's all sorted, else I want to calculate my pivot value. This doesn't make any sense because you haven't seen my quicksort tutorial. Set it to whatever value in the array has the index that is equal to right, and then we're going to go int pivot location is equal to partition array, which is a method I'm going to call below. Go left, right, pivot. And then, like we talked about before, we're going to do a quick sort so that we're partitioning smaller and smaller parts of our array each time we cycle through. Here I'm going to do pivot location plus 1, and here we're going to do right. And that just means we got to do partition array, the method for this. Quick sort's pretty tiny, isn't it? When it doesn't have all those comments and all that extra stuff. Public int, partition, and then these are all going to be integers, of course, that are passed in here. And then just to review, left pointer, going to be wherever the value of left is, minus 1, because we're going to increment it here in a second, and it's actually going to start on the outside of the array. Right pointer is going to be whatever the end of the array is, because we're going to be partitioning. We're going to cycle through this as long as we have to until the whole thing's sorted. We're going to say while the array, we're going to increment left pointer, so that we're actually getting a value out of the array, not -1, which doesn't exist in the array. Yeah, I figured what the heck, I might as well provide a review of some of this stuff that I've been doing. Cycle through the right pointer as long as it doesn't equal to 0, and the array decrement right pointer is greater than pivot. Cycle through there, find pieces that need to be partitioned to the opposite side of the array. If left pointer is ever in a situation where it's greater than or equal to right pointer, we're going to break out of there, which we have to do because we have this set as an infinite loop, else swap those values. You see how efficient this is. And then swap left pointer with right and return the left pointer. And there we are. I think I did all that right. Let's come up here and find out. So back inside of main, and we no longer need these guys because we're going to be using the quicksort. Throw in these timing mechanisms here. Just to show you how efficient it is, I'm going to chuck this up to 100,000 and chuck this up to 200,000. Test, algo 2. Here we're going to do the quicksort. Where is that quicksort? There it is. Set into 0. Test algo 2. Pass in the number of items in the array and execute. And you can see it cycled through 100,000 items in 41 milliseconds. Let's take this up to 4 just by changing this to 4. File save, execute. And it only took 44 milliseconds to jump up to 400,000 or 300,000 in this situation. So there's a rundown of Big O notation and an explanation and a view and look at it from numerous different angles. Leave any questions or comments below. Otherwise, till next time.